everyone. My name is Shobha Sharma from ABES Engineering College. In today's lecture, we will discuss about sampling theorem. So the topics will be like this. What is sampling? Why do we need sampling? And what is sampling theorem? Okay, so let's begin. Okay, so hmm, what is sampling? Sampling is nothing but a conversion of a continuous time signal to a discrete time signal. But a question arises that when all the real time signals we encounter in our daily life are continuous time signal, then why do we need to convert them to discrete time signal? Why do we need to study even the discrete time signals? The answer is the extensive use of digital technologies. When you look around, you will find various digital technologies and implementation which actually need digital data or discrete data to process. They cannot process the continuous time signals. So, for example, the most widely used digital technology is computers. They are completely digital data based. They can process only the digital data. So, in today's scenario, if we have something discrete in nature or digital in nature, then we can process that data easily using the digital technologies. So sampling serves this purpose. Sampling basically converts, or we can say reduce, the continuous time signal to discrete time signal. Okay, so to better understand the process of sampling, let's take an example here. This is a message signal which is represented as empty, which is a message signal which is carrying the information we want to process. Okay, so it is a continuous time signal. That means it has values at every instant of this time. Okay, now one thing must be noted that this is a band limited message signal. What is a band limited message signal? A signal whose frequencies lies in a fixed range. That means this message signal empty, whose frequency domain representation is something like this, has frequencies ranging from minus omega m to omega m. And beyond these points, like after omega m and after this point minus omega m, the frequency components are zero. Okay, so such signals are known as band limited message signal. Okay, at the end of this lecture, I will tell you why are we taking band limited message signal for this sampling purpose. Okay, so for now, just remember that we are taking a message signal MT whose Fourier transform is represented as m omega, and it can be plotted like this. Okay, so this omega m is the maximum frequency component of this message signal MT or m omega. Okay, that means if MT has multiple frequencies, then out of all those frequencies, omega m is the maximum frequency component. Okay, so now we have this message signal. Now we will provide this, sorry, we will provide this message signal to a device known as sampler. Okay, sampler is acting as a multiplier. Okay, so it is multiplying these two signals. One of them is the continuous time message signal, and the other signal we can see here is a periodic signal. It is a periodic impulse train. Okay, it has impulses, or we can say delta function at different time instants. Okay, at TS, 2TS, 3TS, that means after every TS, this impulse is repeating itself. Okay, so it is a periodic impulse train which can be represented like this. CT is equal to summation of these different delta functions, okay, defined at these particular time instants. Since it is a periodic signal and which is repeating after every TS, then we can say this TS is a fundamental frequency of this periodic signal or sampling period or sampling interval. Okay. And omega s, which is angular frequency, also known as sampling frequency of this periodic impulse train, is equal to 2 pi by Ts. Okay. So these two signals we are feeding to the sampler, which will multiply these two signals, and the result will be something like this. Okay, which is represented as ST, which is nothing but a product of MT and CT. Okay, now here this dashed line is the envelope of the message signal. Okay, it is showing the variation in amplitudes of variation in amplitude of the message signal MT. Okay, so when we multiply these two signals, what we get here, we get different samples defined at the positions where the delta or impulse function is defined. Okay, so at this particular time, that means at origin, we get this impulse whose weight or strength is equivalent to the sampled value of the message signal MT at this particular time. Okay, at TS, whatever the value of MT is the strength or weight of this particular impulse. Okay, so at different time instants where the impulse function is defined, we will get the sampled value of our message signal MT. Okay, so this is the ST, or we can say this is the sampled signal. Okay, so this is the ultimate aim of sampling, to convert this continuous time signal to this discrete time signal. That means now instead of every instant of time, the message signal has sampled value at discrete points of time. Okay, now the next thing is, now we want to see the frequencies present in this signal. That means we want to uh, find out the Fourier transform of the signal ST, okay, which is represented as S omega. Now, since this ST is the product of MT into CT, then we have to find out the Fourier transform of this complete equation. In order to uh, find that Fourier transform, we need to know a property, a very important property of Fourier transform, which says that if two signals are multiplied in time domain, then they will be convoluted in the frequency domain. Okay. Okay, so here there is a mistake. This is not a plus sign. Here, the convolution operator should be here. Sorry. Please correct it. This is not a plus sign. It is a convolution operator. So the Fourier transform, the property of Fourier transform says that if two signals are multiplied in time domain, they will be convoluted in the Fourier domain or frequency domain. Okay. Now this m omega is the Fourier transform of MT, and the C omega is the Fourier transform of this CT, that is, which is the periodic impulse train. So these are convoluted in the frequency domain. Now C omega can be written as like this. Okay, it is a delta function defined at different frequencies. Okay, now put this value of C omega in this equation, and then we get this particular equation. Okay, now take this omega s out of the brackets, and we can rewrite this equation like this. Now, in the previous slide, we saw this omega s, which is the sampling frequency, is equal to 2 pi by Ts. Okay, so on putting this, the value of this omega s, we get 1 upon Ts. Okay, now to simplify this convolution, sorry. Okay, now to simplify this convolution, we will use a property of Fourier transform, which says that if a function of time is multiplied, or sorry, with is convoluted with delta function, then it gives us the function defined at discrete time instants where the delta is defined, where the delta function is defined. Only we will get the values of that particular function at those points where the delta is defined. Okay, so using this property, we simplify this equation and we get this particular equation where we are getting the spectras, the frequency domain centered at those particular frequencies where the delta function was defined. Okay, now let us expand this equation for different values of n and we get this equation. Like for n is equal to 0, that means at origin we get m omega. For n is equal to 1, we get this particular term. For n is equal to minus 1, we get this particular term and so on. Okay, so the waveform of S omega will look like this. Okay, will look like this. So here we are getting different spectrums centered at different frequencies. Okay, like this spectrum is centered at origin. This spectrum, when we put n is equal to 1 in S omega equation, we get this spectrum which is centered at omega s. When we put n is equal to minus 1, we get this particular spectrum which is centered at minus omega s. Okay, so in this way, we get different spectras which are centered at different frequency points where the delta function was defined. Okay, now see this particular triangle. Okay, initially I defined sampling like it is a process in which we convert continuous time signal to discrete time signal. Now, after processing the complete signal, we are required to reconstruct our original signal, which is a continuous time signal. Okay, in order to reconstruct the signal, we need to satisfy a property of sampling, which says that the sampling frequency, which is omega s, it must be greater than or equal to twice of omega m. Omega m is the maximum frequency component of the message signal. Okay, so we need to satisfy that particular condition if we want to reconstruct our original signal back. Okay, so we will see these two cases here. This particular waveform belongs to the case where omega s is greater than twice of omega m. Okay, see here. This point is omega s. This point is omega m. Okay, this is the spectrum of the original message signal, original continuous time message signal, which was centered at 0, whose maximum frequency component was omega m. Okay, so this point is omega m and this is omega s. Now, similarly, when we put n is equal to 1, this particular spectrum shifts towards right and centered at omega s. Okay, so this way, this point becomes omega s minus 1, omega s minus omega m, and this point becomes omega s plus omega m. Okay, so to extract this particular triangle, which is the Fourier transform of our original message signal, it is required that either these two consecutive spectras have some gap between them or they can even touch. They can even touch with each other. In both these cases, we can easily extract this particular spectrum from the complete waveform. Okay, from the complete spectrum, we can extract this particular spectra to reconstruct our original continuous time signal. Okay, so in this case, we see that this gap between these two triangles is known as guard band. Okay, and its value is equal to omega s minus, sorry, omega s minus omega m. For this to achieve, omega s minus omega m must be greater than omega m. Okay, and on simplification, we get omega s should be greater than twice of omega m. Okay, then we can easily extract this particular triangle. In another case, if the two triangles are touching each other, that means if omega s minus omega m is equal to omega m, okay, which implies omega s is equals to twice of omega m. So in this case also, we can easily extract this particular triangle and we can then determine inverse Fourier transform to reconstruct our original signal. Okay, so these two cases are known as oversampling and perfect sampling. So in both of these cases, we can easily reconstruct our original signals. But what if these two triangles overlap with each other? Okay, so if these two triangles will overlap with each other, then it becomes difficult to extract that particular triangle because it will have information of left and the right triangles also. Okay, let's see that case also. So see this waveform. Here we can easily see that this triangle, which is centered at 0, is overlapping with the left triangle as well as with the right triangle. So it will have content of this triangle and this triangle. So whenever we extract this particular triangle, whenever we try to extract this particular triangle, it will not it will not represent the original signal accurately, as this has some information from the adjacent triangles also. So this case represents this particular condition when omega s is less than twice of omega m. Okay, and this case is known as undersampling. Okay, so in out of these three cases, that means the oversampling and the perfect sampling case, these two cases can easily give the signal, the continuous time signal we were taking initially, the original continuous time signal. So these two cases can easily give the continuous time signal back. But this case, that means the case of undersampling, will make the reconstruction difficult for us. Okay, so using these three cases, we can define sampling theorem. A signal can be represented in its samples and can be recovered back when sampling frequency, that is omega s, is greater or equal to twice of omega m, which is the maximum frequency component present in the signal. Okay, so this is a Nyquist sampling condition which must be satisfied in order to reconstruct our original signal. Okay, so this was all about sampling theorem. Here are some references.